Okay, now we are at the ever popular box problem. Okay, so how the box problem works is I've given you all the directions over here in case you want to read it, but I'll summarize it for you. Basically, what's going on is you got a sheet of paper or cardboard or metal or whatever you want to call it over here. You're going to cut four squares from each corner. Okay, I don't know what the size of those squares are going to be. Nobody does. But all I know is whatever size square you do end up cutting, they have to be the same on each of the four sides. Okay, one square can't be bigger than the other. So what'll happen is when you cut these squares and you remove them from the sheet of paper or whatever material you have, you end up with this picture over here. So obviously now all the squares are gone. Well, when all the squares are gone, what you'll notice is if you were to take these remaining, I guess we'll call them flaps, and if you were to kind of fold them about the dotted line, you would end up with this picture over here. Okay, you would end up with the box. Okay, so this, and this would end up being these sides over here. On the bottom, you don't see it, but that's the base. The only thing that this box doesn't have, as you can probably picture from here when you fold it up, is that it won't have a top, okay? So basically it'll have five sides, it'll have the four on the side and one on the bottom, but it won't have that top part, okay? Um, so that's basically how you go from the paper to the box. All right. Now the thing is, every box, when you calculate it, is going to have so much volume. That's how much stuff that it can hold on the inside. Okay. If you're not sure what volume is, think about filling box. Think about filling this box with like water, assuming it doesn't leak, and think about how much water it can hold. That's the volume. All right. Okay, so back over here then. So the idea then is perhaps if I were to cut like really big squares, okay, all right, you would still end up with a box over here, except now the box would look different because the size of the squares that you cut would be bigger than the other ones, okay? And I don't know exactly what it would look like, but it would look something like this, all right? So let me try to draw it for you. Not the world's best artist, so you're just going to have to use your imagination if you can't tell. Okay, so basically what you see over here is the idea that if I were to cut bigger squares over here, I would still get a box, but look at how this box is different than that box. This box is obviously wider, and this is not as wide, but it also has less height, and this one has more height. Okay, either way, this box has volume, and it can hold so much water, just like this box has volume, it can hold so much water. Which box can hold more water, that's kind of what we're trying to determine here. Okay, so it turns out for any sheet of paper or whatnot, there is a specific size of the square that you can cut away so that when you create the box, it'll end up being the box that holds the most volume. So that's the goal here, for you to kind of get to that point and calculate it and figure it out. Okay? All right. So let me just erase all this so that we don't get too confused here. So to figure out what that size square should be, we're going to start out by filling out the diagram, making sure you know all the parts of it, because if you don't know all the parts of it, you're not going to be able to create the equation. Obviously, if you don't create the equation, you're not going to be able to solve this problem. All right? Okay, so it says in this example, you're given a sheet of paper that's 12 feet by 8 feet. Okay, so obviously the 12 and the 8, we're talking about the outside lengths of your piece of paper. It's got nothing to do with the size of these squares over here. Okay, so common sense will tell you the 12 should probably go on the longer side and the 8 should go on the smaller side. So I'm going to label that right now. Okay, I've got the 12 here, I've got the 12 here, I've got the 8 here, I've got the 8 there. All right. Okay, so what we're going to do now is we are going to cut the squares away, okay? But we don't know what size these squares should be, okay? Like what length each of the sides for that square should be. So what we're going to do then is we're just going to call it x right now, okay? Eventually we'll figure out what x should probably be, but for now, since we don't know, we are just going to label it x, okay? So that's how you label that first part over here, okay? Make sure you understand this because when it's your turn, you're going to have to do the exact same drawing for me, and if you can't, then obviously going to take some points off here, okay? So it's very important that you get the drawing right. Okay, so we go from this picture to this one. So what's different about this picture? Well, the squares are gone, okay? Which means now these side lengths over here are going to be a little bit shorter, okay? Now, how much shorter are they actually going to be? Well, let's look at this one going across first. This used to be 12, right? And then what did I do? I removed the two squares. Well, how do the two squares affect this 12 over here? If you look at the x on the bottom, this square has a length of x. That square also has a length of x. So when you're removing these two squares, you're removing x twice from this length of 12, right? You're removing it once here and once here. That means this one over here now, we will now represent as, oops, I probably don't need the line over here. I'll just write it over here. This will be 12 minus 2x. Okay, so keep in mind it's 2x, not single x, which is what a lot of you guys are going to put if you're in a rush or if you're not really thinking about it. But it's actually 2x here because, again, there's two squares that we're taking away. Okay, so 12 minus 2x here and 12 minus 2x there. Okay, using that same logic, we can also say for these sides on the left and the right, it used to be 8, right? But then when I moved the two squares away, that means I removed a width of x here and a width of x there from this original 8. So again, this one over here, this one is going to be, let's see, how should I write it? Should I write it sideways? I guess I'll write it sideways. This one will be 8 minus 2x, just like this one over here will also be 8 minus 2x. Okay. All right, so that's all you really need to fill out here. Again, we're going to take these flaps, we're going to fold them, right? And then we're going to create this box over here. Actually, no, a couple more things we should add in here because it'll make this picture a little clearer. So let's keep in mind that for this picture over here, these lengths, this is where the squares were removed, okay? These are obviously going to be x because that's what I cut away here, right? So x here, x here, x here, x there, x there, x there, x over here, and an x up top. Okay, and now I think this is good. Now we've pretty much filled up all the sides. All right, so next thing we're going to do is we're going to take these flaps, okay, and we're going to fold them, right? We're going to fold them and we're going to make this box over here. Okay, well, what are the dimensions then of this box? Well, let's look at it. When you folded it, okay, so when you fold this, 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 and this part over here is actually the same as the height of your new box. Okay, so the height of your new box is going to be x. This length over here, okay, is your long side, right? That's going to be this part over here. So that's going to be 12 minus 2x, all right? And then lastly, this side over here is actually going to be the same as this one over here, okay? So that's going to be your 8 minus 2x, all right? And that is the dimension of your box. Okay, so now you are done filling out the diagram. Okay, so again, let's look at what we did here. So we started off with the whole sheet of paper or whatever. That means whatever dimensions we started here go exactly here and here. Okay, so 12 here, 12 here, 8 here, 8 here. From there, we're going to remove squares that are a length of x. So this part never changes, okay? you'll see when you do your problems, these numbers are going to change, but these numbers, these x's over here will never change because it's always x. All right. Okay, so we went from this picture to this picture. Over at this picture now, we said these flap links over here, the ones that you're about to fold, these are obviously going to be smaller than the original lengths of the paper. So how small are they now? Well, it's basically whatever these guys were subtracted by 2x. So that's what you see here, 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 and here. Okay. Meanwhile, these inside kind of right angles over here, they're still a length of x. All right. And then finally, we're going to fold this up and create the box over here. And when we do that, the height is going to be the length of the square that you cut away. So that's the x. And then the length and the width over here is going to be the same as what we had over here. That's how we got the 12 minus 2x and then the 8 minus 2x over there. Okay? Okay. Actually, let me just erase those side ones. I don't want you to think that those look like ones. So let me just erase it here, erase it there. Okay. Okay, so hopefully you know what the x is, the 12 minus 2x, and the 8 minus 2x are talking about. All right, next up then, we want to use this information and we want to write a formula that describes the volume of the box, and we're going to call it V of x, okay? Where basically your volume is going to be a function of x. So what does that mean? That means whatever I say V is equal to, all I get to use are x's and numbers. I don't get to use any other letters, okay? So I'm going to say my volume is going to be equal to, now, even before I look at this picture, you should already know for a box, all right, there's only one formula for volume. It's length times width times height, right? Okay, so if you look back over here, length times width times height, that's length, that's width, and then that's height. And you can put it in any order that you want to. So even though I said length times width times height, if you wanted to put the height first and then multiply it by this guy and then multiply it by that guy, it would be totally fine. Okay, as long as you write it correctly, you're good. The order doesn't really matter here. All right, so that means then when I multiply everything together, V of x is going to be equal to 12 minus 2x, 8 minus 2x, and finally just x. Okay, so this is the big formula you need to get correct. If you can't get this formula correct, the rest of the problem gets screwed up. Okay, so always make sure that you get this formula correct. This part right here, this x, it's always going to be x. So you can't mess that up. It's really only these guys that you're going to mess up. And the only real reason you're going to mess this up is because you're going to put a single x here and not a 2x over here. If you put a 2x, I think you should be able to get everything all right. Okay. Okay, so key to the first page then is make sure you fill everything out correctly, and then make sure you're able to use that last drawing to create your formula over here. All right. Okay, let's move on to the next page then and start asking some important questions. Okay, so now that we have our formula, let's try to use it to fill out this table over here and then answer some important questions so that you can get a better understanding of what's going on here. Okay. Okay, so first thing you want to do is use this formula to fill out this table. It's got different parts of this table. It asks you the height, the length, the width, and then the volume at the end. Okay, so when x is equal to 1, so this is the side length of that square that you're cutting away. Okay, it asks what is the height of your box going to be. Well, if you recall, the height of your box is always going to be the same length of the side of the square that you cut away. Okay, so this part's always going to be easy to fill out. The height of your box is always going to be, you know, pretty much your square size. Okay, so 1, 2, 3, 4 over here means it's going to be 1, 2, 3, 4 over here. Okay, pretty simple. Next up, the length. The length is this part over here. Okay, so when you cut away a square of side length 1, obviously you're going to put the 1 in here. do the math, and then figure out what your length is. Okay, so if you look at it, 12 minus 2 times 1, that's going to be 12 minus 2. That'll get you 10. Okay, at 2, it'll be 12 minus 2 times 2, so that's 12 minus 4. So that'll give you 8, and then 6, and then 4. Okay. In fact, let me go back and just kind of fill in the 12 minus 2 part there, just so when you look back at this, you can see where the 10, 8, 6, 4 came from. Okay, so once again, the length is this part over here. Okay, the first time around when I plug in 1, that's going to be 12 minus 2, so that'll give me 10. Okay, the next time around it'll be 12 minus 2 times 2, that's 12 minus 4, so that's how you get the 8. And then when the box size is 3, you're going to go 12 minus 2 times 3, that's 6, so that's going to give you 6. And then finally, at 4, you're going to have 12 minus 2 times 4, so 2 times 4 is 8. 12 minus 8 is going to give me 4. All right? So now we're going to do the same thing for the width, except we're going to use this part over here. Okay, so if you want to write up top, just so you can see it, this is the length part, this is the width part, and this is your height part over here. Okay, so for this part over here, again, if I plug in 1, it's going to be 8 minus 2 times 1, that's 8 minus 2, which is equal to 6. Then you're going to have 8 minus 2 times 2. 8 minus 4 will give you 4. Then you'll have 8 minus 2 times 3. 8 minus 6 will give you 2. And then finally, 8 minus 2 times 4, that's 8 minus 8, that'll give you 0. Okay. So now, to figure out the volume based on these square sizes, all you got to do is take the numbers that you figured out and then multiply them together. Okay, so 1 times 10 times 6, that'll get you 60. 2 times 8 times 4, I believe that's 16 times 4. That should give you, I believe, 64. And then 3 times 6 times 2, that's 18 times 2, which will give you 36. And then finally, 4 times 0, anything times 0 will get you 0. Okay? All right, so those are all your different volumes based on the different sizes of X that you get. The key thing for you to see here that you may not have realized is you might have thought, the bigger this number gets, the bigger that number gets, and that's not true, okay? At some point, the numbers start to drop even though these numbers keep on increasing. So don't think the biggest number you can put in here is obviously going to give you the biggest volume. Not how it works, okay? It's always going to be some number in between here that gets you the best volume over here, okay? All right, so next thing we want to do is analyze the domain. I won't always make you do this for all of your problems. I just want to go over this with you so that you have an idea what's going on here, okay? So again, we're talking about our box that looks, actually that height's pretty big. Let's make it a smaller box, okay? Let's go like that. Okay, so we're talking our box that looks like this. So this is the X part, okay? This was our 12 minus 2x, and then over here, this was our 8 minus 2x, okay? All right, so it says, why can't x be negative? Okay, well, if x was negative here and here, it actually wouldn't be a problem. This would just make these really long, and that's fine. You can have boxes with long widths, or sorry, long lengths and long widths. But the problem with x being negative here is that then you have a negative height, and that just doesn't make any sense. Okay, it's the same reason with why x can't be equal to 0. All right, if x is equal to 0, then you have basically a flat piece of paper. Okay, so for both of these, I would say the reason why x can't be negative or x can't be 0 is because then height can't be negative. Okay, and it would be if x was a negative number. And then for this one, you also would say height can't be 0, because if it was, you would have a piece of paper again, and you wouldn't have the box. Okay. All right, next part it asks you, I had a typo on mine, yours should say 6 on there, so hopefully it does. It says, why can't x be greater than 6? Okay, well, let's look back here at our numbers. So we have 1, 2, 3, and 4. It's saying, what weird thing is going to happen at 6? Well, let's look over here. If I do 12 minus 2 times 6, I'm going to get 12 minus 12, and that's going to already give me 0. So if I have a number bigger than 6, that means, for example, if I had 7, 12 minus 2 times 7, that would be the same as 12 minus 14, and I would get a negative value in here, and obviously your lengths can't be negative, okay? So that's what's going to happen here. In fact, it would make this even worse too, okay? So really, in the situation where your x is greater than 6, that would make your length and width negative, and that can't happen, okay? So can't be negative, okay? What about at x equals the 6? Again, at x equals the 6, that'll make your width negative, that's bad, and that'll actually make your length 0, which is also bad because kind of the same idea as for the height. If you have a height of 0, you have a piece of paper again, right? You don't have a box. Well, same thing here. If you make this length back to 0, then once again, you have a piece of paper again. You don't have a box, okay? So um, length can't be 0, and that's what's going to happen if you let x equal to 6. Also width can't be negative. Okay, so when your x value is more than 6, the length and the width end up being negative, and that's bad. When your x value for the squares is 6, exactly 6, the length ends up being 0, and the width is still negative. Again, both of these still bad. Okay. So then it says, so why did we stop at 4? Okay, so in other words, if 6 is the bad number here, why didn't we stop at 5? Well, let's look back here and see what would happen if we did a 5. Okay, so again, I'm just going to write it on top so we can see it. So if my x was a 5, that means my height would be a 5. Okay, is there a problem with the height of your box being a 5? Nope. You know, tall box, no problem with that. Okay. What about our length? If we did 12 minus 2 times 5, what would we get? We would get 12 minus 10, which is 2. Small number, but it's still positive, so it's still okay. You still actually have some length there, so that's fine. Okay. What about for the width? Well, we'd have in this case 8 minus 2 times 5, and that would be negative 2. And here's where the problem is if we allow x to equal to 5. Okay, it turns out the height's fine, the length's fine, it's the width that's going to end up being pretty crappy. And in fact, it says, why do we stop at 4? Because 4 is the last number you can input in here to get 0. Anything after 4, you're going to get a negative number. Obviously, we don't want this to be negative. Okay, so in this case, when it asks you why did we stop at 4, because anything greater than 4 would make the width negative, okay, and that's bad. And actually, if you look at it closer, I mean, if you look at what happened at 4, 4 wasn't that great either, right? Our volume is 0, okay? The reason our volume is 0 is because when you plug a 4 into the width, yeah, it's not negative, but it's 0, and 0 is just as bad because remember we talked about this before. Whenever any of these lengths are 0, that means you actually have a piece of paper again. You don't have a box. So when it's asked you, does x equal 4 actually work too? The correct answer is no. Okay, your width would equal to 0. So again, that would mean you wouldn't have a box again. Okay, so it asks you what is the practical domain of the function? In other words, what are the x values that you can really use? Obviously, you can plug in any number you want to, and then when you do the math, you'll get some answer, but what's a answer that we can actually use here? In other words, something that's not a 0 or something that's not negative. So it turns out the only numbers that we can really use are anything between 0 and 4. Okay, so even though I could technically plug in a 5, a 6, a 7, a 8, a 9, a 10 into this formula over here, it would not give me an answer that makes any sense. Okay, the only answers that would actually make sense would be between 0 and 4. And when I say 0 and 4, again, what I really mean to say is between 0 and 4. Okay, so if you write that using the inequalities, if you still remember how that works, you would say 0 less than x less than 4. Okay, so I don't want to put exactly 0 because we talked about it before. At 0, that means I have no height. That's bad, but anything past 0 is good. I don't want to put exactly 4 because at 4, this part becomes 0, and that's bad as well. Okay, so this is our practical domain here. And then lastly, this part says determine the optimal value of x that results in the greatest volume of the box. All you have to do is look back at your chart and say, and not say, but and see for all the values that you plugged in, was there one that was bigger than the other? And yes, it looks like 64 is the biggest volume that you can get. Okay, 64 happened at x is equal to 2. Okay, so in this case, when it asks you what is the optimal value of x, you would say it would be x equals 2. What is the greatest volume? Volume would equal to 64. Okay. All right, so that pretty much answers the box problem. Again, what was the purpose of this? Well, all these questions was to get you understanding why you can't plug in certain values of x. Really, the main objective here was what is the best size square that we should cut so that we get the best volume. And it turns out, if you look at our table, that's going to happen at 2, and it's going to give us 64. Now, will it always happen at 2 and give us 64? No. That all depends on what your original size of the paper was. In this case, for a 12 by 8, I can tell you for sure if you cut it at 2, or if you cut square sizes of 2 by 2s, and you will get the best volume. Okay, but if these numbers were different now, if for your problem you ended up with like a, I don't know, 10 by 5 or a 30 by 20, then all of a sudden you're going to have to calculate your own values and see which volume was the best there. Okay. Okay, lastly, what we're going to do is we are going to graph that box equation that we came up with, just so you can see how it relates back to this polynomial chapter that we're focused on. Okay, so again, if you remember, the formula is v of x is equal to I think 12 minus 2x, and then we had, what was it, 8 minus 2x, and then we had x, right? All right, so just like before, first thing you want to do is you want to figure out your end behavior. That means you take all the x parts and you multiply them together, right? So negative 2x times negative 2x will be a positive 4x. Positive 4x, oh sorry, actually negative 2x times negative 2x will be a positive 4x squared. And then when you multiply it by another x, you'll get 4x cubed. Okay, so for 4x cubed, that means our end behavior is going to be down up. Okay. Next thing you want to do is you want to figure out your x-intercepts. So again, that means setting each of these parts equal to 0. This is the easy part right here. This is obviously going to equal to 0 at x equals 0. This one, or these two over here, you just need a little bit of math to figure them out, but it's not too bad. Okay, so when does 12 minus 2x equal to 0? Well, basically you're asking yourself 2 times what is going to give you 12? In this case, that's going to be 6. And then for this middle factor over here, what times 2 is going to give you 8? That's going to be 4. Okay, so 4. Okay, so that means our x-intercepts are going to be at 0, 4, and 6. Our y-intercept, that's when we plug in a 0 and then do the math, right? Well, when you plug in a 0, yeah, this is going to be tough, this is going to be tough, but the key here is what are you going to get when you plug in a 0 over here? You're going to get 0, right? And 0 times whatever is still going to be 0. So I don't really need to calculate these parts because of this factor right here. I already know When I plug in 0, I'm going to get 0. So my y-intercept is going to be at 0, 0. Okay, so just like last time when we do the dots, that means I'm going to have a dot at 0. I'm going to have another one at 4. And I'm going to have another one at 6. Okay, so if you want, let me just draw those dots real fast like we typically do. Dot here, dot here, dot here. Based on your understanding of end behavior, I think you should already have an idea what's going to happen, right? So we're going to kind of hit here. Since this only showed up once, we're probably going to go up to some point and then come back down. We're going to hit 4, we're going to go through it, and then we're going to go down to another point, come back up, and then finish our graph. Okay, so that's the idea here. Okay, so that's where we're going to do our additional points. To help us figure out where this location and that location should be. So it turns out we already know this location. Okay, if you go back to our previous table, if you think about it, one of these values is higher than all the other one. It was 64, right? And it happened at 2. Okay, so really, I don't have to guess here where it's going to be. I just need to plug in the 2. So here's your x, here's your y. I plugged in 2, and I got 64. Okay. This one over here, I don't know where it's going to happen, so this one I do have to figure it out. Right between 4 and 6 is 5, so I'm going to take 5, and I'm going to put it here, here, and here, and see what happens. Okay, so I'll do the calculator for that one, and when I plug in 5, this is what I get. All right, so it turns out I get, oops, let's go back to the pencil here. It turns out I get negative 20 when I plug it back into here. Okay, so let me put those dots on here so you can see it. This time, let me use a different color so you can see it a little easier. And I will erase this part over here since I'm going to be a little more exact now. Okay. Okay, so at 2, I'm at 64. Again, this is what I was talking about before. If I actually try to go 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way to 64, obviously it's going to be like way above this part over here. Okay, so instead of doing that, I'm just going to call 64 somewhere like right here. So this will be like 264. And then that means when I do my next point at 5, negative 20, I'm obviously not going to put negative 20 all the way down here. If I proportion it, 20 is about like a third of this. So a third of this distance maybe is like somewhere right there. Okay, so I'll just put my point somewhere over here at 5, negative 20. Okay, and then when I connect the dots then, this is what it's going to look like. Okay, so I got my end behavior, and then I'm going to hit this dot, going to come back down, going to cut through here, going to connect to that dot, going to hit my intercept again, and I'm going to finish up. Okay, so this is pretty much your graph for this guy over here. Now, how this relates to our problem is, for our problem, we basically said, well, this graph, all these, let me go back to this. Okay, so all these dots on this graph that you drew, it's supposed to represent volume, okay, because this is a volume function, right? Okay, well, these are all negative, right? I don't want negative volumes. That doesn't make sense when you're talking about a box, okay? So when we were talking before about why can't x be negative and stuff, we're basically saying, even though this is the entire graph when you draw it, really for our purposes, we want to exclude this part because this is negative. Same thing over here, this part is negative 2, so I want to exclude that part. And this part is good, this is positive, right? I like this. Except the problem with this is when you, in order to get these values over here, when you plug in, for example, 7 in here and 7 in here, um, this is going to end up being negative, that's going to end up being negative, and these two negatives multiplied together, that's how this whole thing stays positive. So even though this part of the graph is where I like it to be for a volume, even though it's in the positive section, the way that it became positive, using like two negative side lengths, that doesn't make any sense either. Okay, so realistically, even though this whole graph represents this function over here, in terms of like real life applications, I can't use this part, I can't use this part, I can't use this part. Really, only this part was the usable part for my word problem, okay? And out of this entire usable part, what I discovered was that this point over here was where I would get my best volume. Okay, so that's what we did on the previous page. Now, don't worry, I won't make you graph this for the box problem, because really you don't need to graph it to be able to figure out where the best volume happens. But again, I just wanted you to see how this relates to our polynomial chapter. So this entire function obviously is a polynomial. Obviously, you are able to graph it using the techniques that we talked about earlier. Okay, the only difference here is that since we're talking about a real life scenario, we had to be smart about it and realize even though like this is our entire graph over here, realistically we can't use this part, or that part. So really we got to look over here to see where our best answer is, and that's what we did for the problem. Okay, so I hope this makes sense. You only get one example because as you can see it takes a while to explain. But when you do it, it should go a lot faster because you don't have to explain any of this stuff. You just have to know how to do it. Okay?